Example 6. Just a quick word of warning. This particular example is very heavy on the algebra, so if you haven't brushed up on your exponential and logarithmic rules for algebra, those are going to come back here. So you may need to review those separately if you're not following what's happening algebraically at the end of this problem. For time t greater than or equal to 0 in days, the rate at which photosynthesis takes place in a leaf of a plant, represented by the rate at which oxygen is produced, is approximated by P of t equals 100 times e to the negative 0.02t minus e to the negative 0.1t. When is photosynthesis occurring fastest, and what is that rate? So since this function represents the rate at which photosynthesis is occurring, if we're looking for the fastest rate, we're looking for the maximum of this function. So not only are we looking for the maximum in terms of the global maximum, so the actual rate that's the largest, but also when it's happening. So we need both the independent and dependent value once we've found our maximum. So here, again, we're going to start by finding our first derivative to identify any critical points. So here, my first derivative of this function, I'm going to have a 100 on the outside from my constant multiple rule. Now here, I'm going to have to do a chain rule where my z is negative 0.02t, so my dz dt is negative 0.02. So the derivative here is negative 0.02 e to the negative 0.02t minus, and then again, I have to do another chain rule for my second term where z is negative 0.01t. So my dz dt is just negative 0.1. So minus negative 0.1 e to the negative 0.1t. So my first derivative looks like this. Notice that this is a negative and this is a minus, so those can cancel. So to make my algebra a little bit easier, I'm going to multiply this 100 through to both terms. So that tells me that my derivative is going to be negative 2 e to the negative 0.02t plus 10 e to the negative 0.1t. And I want to know, when does that equal 0? Now here, I notice that I cannot factor out the e term because it doesn't have the same power. If both of these terms had been e to the t with the same constant in front, then I could factor it out. However, because they have different powers, I can't factor it. So now I need to use some algebra to try to solve for t. So I know that eventually I'm going to have to take natural logs to get that t out of the power. But the way it currently stands, I can't use natural logs. First, because the first term is negative, and natural log is not defined for negative numbers, but also because I can't just start taking the natural log until I have a single term with a single variable. So what I want to do here is I want to add the first term over to the right. Doing so is going to give me 10e to the negative 0.1t equals 2e to the negative 0.02t. Now, I want to try to combine like terms. So what I'm going to do is I'm going to divide both sides by 2. That's going to simplify my constants. In doing that, I'm going to get 5 e to the negative 0.1t equals e to the negative 0.02t. Now, I'm going to divide both sides by this e term. So e to the negative 0.1t and e to the negative 0.1t. On the left, it will cancel, leaving me with just a 5. Now, on the right, I need to use an algebra rule. If you have the ratio of two functions that have the same base, which I have here, then I can subtract their powers and write them with a single base. So the single base that I have in both is e, and I'm going to take the top power minus the bottom power. So negative 0.02t minus negative 0.1t. The negatives are going to cancel, and this is going to result in 0.8t when I simplify that. So that means I can write the ratio of this function as e to the 0.8t. So I needed to use this algebra fact in order to simplify this enough where it's now at the point where I can use natural logs. So here, if I take the natural log of one side, I have to take the natural log of both sides. So the natural log of 5 equals the natural log of e to the 0.8t. Again, one of my natural log rules is if you take the natural log of something raised to a power, you can bring that power out front. So I'm going to rewrite this as 0.8t times the natural log of e. But remember, the natural log of e just equals 1, and anything times 1 is just itself. So now I can divide both sides by 0.8. That leaves me with my final answer here of t equals the natural log of 5 divided by 0.8. So that's my critical point. That's the value of t, which is going to make the first derivative equal to 0. Now, at this point, I don't know if that's the point that I need. So I know that my restriction was that time had to be greater than or equal to 0. But if I were to graph the original function, I'd be able to determine if my critical point was a maximum or a minimum. So if you were to graph the original function on a calculator or on a computer, you're going to get something that looks like this. So you can see that your critical point is going to have to be a maximum. So now I know the when. When is the photosynthesis occurring the fastest? At t equals the natural log of 5 divided by 0.8. However, I also want to know what that rate is. So I have to go back up and find the corresponding dependent value. So again, I'd found my critical point to be t equals the natural log of 5 divided by 0.8. That answers the first part of the question. When is the photosynthesis occurring the fastest? That gave me the independent value. But I also want to know what is that rate, that fastest rate that I can achieve. So I need to take this and I need to plug this back into my function. So if I do p of the natural log of 5 divided by 0.8, and I crunch that number, that's going to give me 14.27. So that is the global maximum. That is the largest rate that this can be achieved from this function. So here again, I was able to find the global maximum, and I can do that using what I've learned from this section.